In the early 20th century, machines reshaped daily life. Automobiles rattled down unpaved roads, factories hummed with possibility, and engineers stood at the center of modern optimism. This documentary explores one man whose inventions quietly transformed transportation and food preservation. Thomas Midgley Jr. rarely sought fame, yet his ideas touched nearly every engine and refrigerator. His story is one of ingenuity, ambition, and consequences that still echo today. At the core of Midgley's professional journey was a straightforward yet deeply significant conviction. The answers to mechanical challenges could be uncovered through the principles of chemistry. While others noticed sounds or experienced vibrations, he perceived problems on a molecular level. His contributions served to connect the worlds of laboratories and workshops, uniting test tube with engines. To fully appreciate the significance of Midgley's accomplishments, we need to return to a time when engines faced difficulties with knocking, refrigerators emitted dangerous chemicals, and the conveniences of contemporary life relied on innovations that had not yet been conceived. By the 1910s and 1920s, innovation progressed rapidly, but failures occurred even more swiftly. Automobiles frequently broke down, engines destroyed themselves, and cooling systems utilized hazardous chemicals. Advancements required bold and daring experimentation. Midgley rose to prominence within this tumultuous environment, driven by an innate curiosity and backed by influential industrial organizations hungry for new discoveries. His innovations would soon pave the way for widespread mobility and improved refrigeration safety, though the consequences of these advancements were not yet recognized. This is not simply a story of invention, but of the unintended influence engineers can wield. Midgley's ideas spread rapidly, copied worldwide, and normalized almost overnight. Their benefits were immediate and visible, their dangers hidden and delayed. As we begin, keep in mind the dual nature of technical progress, because Thomas Midgley Jr. embodies both its brilliance and its blind spots. Few individuals shaped the 20th century so profoundly without public recognition. Midgley never became a household name, yet his chemical decisions influenced engines, air, and food on a planetary scale. To tell his story accurately, we must follow his work chronologically, understanding not just what he created, but why those solutions made perfect sense at the time. The story starts with the beginning of Midgley's life, during a time when science offered the hope of bringing order to a chaotic world. From his schooling to his initial experiments, his journey shows how a pragmatic problem solver grew into a key figure in the field of industrial chemistry. The foundation built during his early years equipped him to tackle challenges that had confounded whole industries. Thomas Midgley Jr. was born in 1889 into a world already fascinated by invention. His family valued practical engineering, and Midgley absorbed early lessons in mechanics and problem solving. Unlike theorists drawn to abstraction, he gravitated toward applied science, where results were measured in smoother machines and fewer failures, not equations alone. After formal training in mechanical engineering, Midgley entered industry at a moment when chemistry and machinery increasingly overlapped. Engines failed not just from poor design, but from fuel chemistry itself. His education prepared him to think across disciplines, a habit that soon set him apart inside research teams dominated by narrow specialties. Midgley joined General Motors during its rapid expansion. GM wanted reliability, power, and consumer confidence. One persistent issue undermined all three: engine knock. This violent, uncontrolled combustion limited compression and threatened engine longevity. Engineers tried mechanical fixes, but the problem resisted traditional solutions, opening the door for chemical experimentation. Engine knock was more than noise. It wasted fuel, reduced performance, and damaged parts. If left unsolved, it would restrict automotive progress. Midgley recognized that combustion itself needed taming. Fuel composition, not engine geometry, became his focus. This insight marked a turning point in automotive engineering philosophy. Working with chemist Charles Kettering, Midgley tested hundreds of additives. Some improved combustion slightly, others failed disastrously. The process was exhaustive, methodical, and often dangerous. It reflected an era when safety standards were minimal and progress demanded personal risk from researchers. Through persistence rather than luck, Midgley discovered that tetraethyl dramatically reduced engine knock. The effect was immediate and measurable. Compression ratios increased, engines ran smoother, and automotive performance leapt forward. To executives and consumers, it seemed like a miracle solution delivered by chemistry. At the time, the dangers of lead were known but poorly regulated. Midgley himself experienced lead poisoning during development. Still, commercial pressure outweighed caution. Leaded gasoline offered an inexpensive path to better engines, and the industry embraced it eagerly. By the early 1920s, Midgley's reputation was cemented. He had solved an engineering riddle that stumped an industry, but his chemical curiosity did not stop with fuel. A new challenge soon emerged, equally disruptive and equally dangerous: refrigeration. Leaded gasoline quickly became widely used in international markets. It enabled engines to attain increased durability and performance, transforming both transportation and trade. Extended journeys, larger vehicles, and innovative designs all became possible. For consumers, the advantages were clear. For engineers, Midgley's creation established a new benchmark for the integration of chemistry and engineering. To reassure the public, Midgley famously demonstrated the safety of tetraethyl lead by inhaling its vapors briefly during a press event. He later paid for this exposure with illness. Such demonstrations reflect the era's optimism and underestimation of long-term toxic effects. Although public health advocates gave early warning, leaded gasoline was widely used worldwide for numerous years. This enabled cities to operate cars and trucks on a scale never seen before. Midgley tackled the issue precisely as the industry framed it, with minimal motivation to explore the concealed external consequences. As engines grew quieter, a different domestic hazard required focus. Early refrigerators operated using poisonous gases such as ammonia and sulfur dioxide. Leaks from these appliances claimed lives. A refrigerant that was safe, non-flammable, and non-toxic became a necessity. Chemistry once more provided a solution. Midgley turned his attention to synthetic compounds. By systematically modifying hydrocarbons, he searched for a molecule that could absorb heat efficiently without harming users. This work required deep understanding of molecular behavior rather than mechanical design. The result was chlorofluorocarbons, later sold as Freon. These gases performed exactly as needed. They were odorless, non-flammable, and seemingly harmless. Refrigeration finally became safe for homes, transforming food storage and urban life almost overnight. Midgley again demonstrated confidence publicly, inhaling Freon and exhaling to extinguish a candle. The gesture symbolized victory over a dangerous problem. Refrigerators became commonplace, reshaping diets, commerce, and public health throughout the industrialized world. By the early 1930s, Midgley stood at the peak of industrial success. His solutions powered cars and preserved food. Few engineers could claim influence over both transportation and domestic life on such a scale. Yet the story was far from complete. The world welcomed Midgley's innovations with great enthusiasm. Manufacturing facilities adapted, urban areas grew, and the economy progressed remarkably. The short-term advantages outweighed any persistent concerns. Professionals and leaders in the industry praised the evident achievements while overlooking the concealed risks. Unbeknownst to most, lead accumulated silently in the environment. Air, soil, and bloodstreams absorbed its presence. These effects unfolded slowly, beyond the time horizon of industrial planning. Responsibility diffused across companies, products, and consumers. Similarly, CFCs floated upward into the atmosphere, inert at ground level but destructive high above. Decades would pass before scientists connected them to ozone depletion. Midgley could not foresee this chain of consequences, with the knowledge available at the time. These blind spots reveal how problem-solving frameworks guide outcomes. Midgley optimized for immediate safety and performance, not planetary systems. His success exposes the limits of narrowly scoped engineering objectives. By the late 1930s, Midgley's health declined. He contracted polio, leaving him severely disabled. Ever inventive, he designed a system of ropes and pulleys to help himself stand from bed, applying engineering even to personal hardship. Tragically, in 1944, Midgley died after becoming entangled in this device. The accident marked an abrupt end to a life defined by technical solutions. His death symbolized both ingenuity and vulnerability. At his death, Midgley was celebrated for progress, not questioned for side effects. Society lacked the tools to evaluate long-term environmental impact. Judgment would come later, shaped by new science and new values. The narrative he shares prompts contemplation. How many contemporary advancements follow a similar pattern? Addressing pressing issues while inadvertently generating future challenges continues to be a core dilemma in the field of engineering. In the latter half of the 20th century, evidence mounted against leaded gasoline. Studies linked lead exposure to neurological damage, especially in children. Governments slowly acted, phasing out leaded fuel across most of the world. Similarly, atmospheric scientists uncovered the role of CFCs in destroying the ozone layer. The discovery shocked policymakers and industries alike. International cooperation followed through the Montreal Protocol, banning many of Midgley's refrigerants. These responses demonstrated humanity's capacity to correct course, albeit slowly. Midgley's inventions forced society to confront the unintended scale of technological influence. Importantly, blame cannot rest on one individual. Midgley worked within the norms of his time, with limited data and immense pressure for results. His story illustrates systemic issues in innovation, not personal malice. Cleaner fuels and safer refrigerants available today exist due to the insights gained from Midgley's contributions. Nowadays, engineers integrate life cycle analysis and environmental simulations into their design methodologies. The arc from invention to consequence underscores the responsibility embedded in technical expertise. Midgley's legacy helped define modern environmental awareness by revealing what happens when the externalities are ignored. This reckoning reshaped engineering ethics, regulations, and public expectations. Problems are no longer isolated, they are interconnected systems requiring broader vision. Reflecting on the past, Midgley stands as both a warning and a guide for future innovators encountering similar obstacles. Thomas Midgley Jr. changed the world twice, solving problems few others could. His work enabled modern transportation and safe refrigeration, foundational pillars of contemporary life. Yet those same solutions revealed the limits of human foresight. His legacy teaches that technical success must be measured beyond immediate performance. Midgley was neither villain nor hero, but a product of his time. His story reminds us that progress is never neutral, and every invention writes a future chapter. As technology advances quickly in the modern world, Midgley's life stands as a poignant reminder of the necessity of humility. Tackling the problem at hand is only the initial step. The real challenge lies in understanding its long-term consequences. Modern transportation and refrigeration owe much to one man's chemistry. Remembering Thomas Midgley Jr. means remembering both the power and responsibility of engineering genius. His legacy endures in every smooth-running engine and chilled shelf, a quiet testament to innovation's double-edged nature.